Okay, so I'm sorry about the other video cutting off so abruptly. Actually, my computer froze, and I actually had to do some recovery on that file, some recovery commands. So if the audio sounds jumpy a little bit, I do apologize for that. But my brand new computer froze on me, so that's a lot of fun. But let's go ahead and finish this up. We actually didn't have all that much left. Okay, so we were talking about average velocity of particles. And so I think at the end you can hear me talking about the slide, but you can't actually see it. So I'll go over it again. So what I was saying was, if we look at heavier atoms versus lighter atoms, so the average velocity of a heavier atom, so say oxygen for instance, is going to have a slower average velocity compared to a lighter atom. So for instance, oxygen has maybe a molecular velocity around there. Okay, so an average molecular velocity, whereas hydrogen, okay, and helium, much lighter atoms, and you can kind of see other things in the middle, are going to have much higher velocities, or average velocities. So root mean velocity is what we're talking about. Okay, so basically just if they have the same amount of energy, okay, the same temperature, but they're lighter, they're going to move faster. Okay, so no real big mystery there. So heavier atoms are going to move slower. It's like having a big truck taking off, or versus like, I don't know, an Indy car or something like that. Okay. Here's a pretty a root mean squared calculation for you. You just have to plug in the numbers. I feel like you can do it without me going over it too much. So use your formula. Okay, so remember and you just need R, which remember you need in units of energy. T you need in terms of Kelvin. And then M is just the molar mass of whatever you're talking about. So in this case, oxygen. Okay, so we can just plug in our numbers here. So 3 times 8.314 joules over K per mole. Okay, times the temperature in Kelvin. Okay, then over the molecular mass of oxygen in kilograms. Okay, then from there, and the reason you need kilograms is to match with joules, and it'll end up with meters per second. Okay, so really not too tough of a problem. Okay, but just know how to use that formula if I give it to you. The only thing here is knowing that you need kilograms here. Okay, so just the last couple slides here, then we'll be done. I think there's literally 2 or 3 left. Unfortunately, like I said, my computer crashed. So let's go ahead and finish this up. Okay, so gas diffusion and effusion. So just some definitions here, basically. So diffusion is the gradual mixing of molecules of different gases. So this is if we put 2 different gases into the same container, or even just let them into a room or whatever it is. Okay, it's the diffusion. So diffusion is the gradual mixing of molecules in different gases. And this will just happen over time. Okay, so just all on its own, gases will diffuse, because remember, a gas will fill its container. So if I have 2 gases in a container, well then they're both going to fill the container. So they'll just mix evenly, all on their own. The second one, effusion. Okay, so this is the movement of molecules through a small hole into an empty container. Okay, again, so it's going to fill the volume of the room. So if that room or that space contains some empty space with a hole that gas can get into, well, it's going to consider that part of the space, part of the room, part of the volume. Okay, so effusion is moving through a small hole. Okay, so diffusion is just mixing, effusion is actually passing through something. Okay, so molecules effuse through holes in a rubber balloon. Okay, so this is why over time your balloons might lose some of their helium, and they may deflate a little bit, okay, because there are tiny pores in those balloons, and oxygen and helium are going to exchange until eventually you don't have a fun party balloon anymore, you just have sort of a dead balloon. Okay, so an example here, we have rate is equal to the moles over time, which is proportional to the temperature, and is inversely proportional to the molecular mass. Okay, so if we have more temperature, those molecules are going to move faster, so of course they're going to effuse faster. If we have a bigger molecular mass, well, of course those molecules will move slower, okay, and so they'll effuse faster. Okay, so down the bottom here it gives us a note that helium effuses more rapidly than oxygen at the same temperature. And that's because their molecular masses are so different. Okay, and this is just an example of kind of an effusion here. So we have basically a glass cube here, or a glass rectangle, kind of a cubic rectangle, basically a container. Okay, and there's sort of a divider with a hole in the middle. And what you see is a bunch of gas particles moving around, and every once in a while, one of them manages to go through the hole, and eventually, given enough time, they would eventually fill the entire container. Okay, so this is the last thing I want to say about gases, is that most of what we talked about, in fact, everything we talked about was at ideal conditions. Okay, so just keep in mind that when you're using the ideal gas equation, the real world varies from that somewhat. Okay, so when we're talking about ideal conditions, understand that we don't live in an ideal world. Okay, so under non-ideal conditions, real gas particles do have volume. Okay, so the meaning of the gas, meaning the volume of a gas is the volume of the gas particles plus the volume of the container. Okay, so real gases do have volume. In other words, the particles in the gas do have a volume. Okay, so they do have intermolecular forces. In other words, if they didn't have those, a gas could not become a liquid. So how would, even as we lower the temperature, how would, for instance, water vapor eventually condense back down into water if there wasn't some interaction between the two, some intermolecular forces, which just means an attraction between two molecules. Okay, so this implies that there are attractions between gas particles, and therefore collisions are actually not elastic in nature. So when two molecules smash into each other, there actually is some energy exchange, including some energy loss. And pressure of a gas is not just due to the gas particles colliding with the container walls, so there's more to it than that. It has to do with them colliding with themselves. It just there's lots and lots to it. Okay, more than just colliding with the container walls. Okay, but just keep in mind that we were talking about ideal gases, but in the real world, we're dealing with real gases, not necessarily in ideal conditions. Okay, so that is the end of the lecture. I know this one, kind of the tail end of this video, it's literally 7 minutes, so sorry about that. Yeah, look at my Surface locked up on me, and I had to reboot it, and I basically lost my file and had to do some recovery. But so again, if the audio on the previous one sounds choppy, hopefully it's not too bad for you guys. Okay, I will talk to you next time.